Hey everybody, I hope you're all doing well. I hope you're all staying safe. Welcome to AppSec 101 at DEF CON 29's AppSec Village. Over the next 30 minutes, let's take a journey from engineer to hacker to appreciate the value that application security adds to modern secure software development. But before we jump into it though, I do want to call out that this is a 101 level talk, approachable to people who may be unfamiliar with application security. It's what I like to call cyber fried chicken. Why do I call it that? Well, let's just take a quick bite and find out. Just like you can eat a single chicken wing and say you've tasted and eaten chicken, it's just a small part of the whole chicken. It's part of the whole bird. You cannot say that you've eaten an entire chicken. You cannot say you've eaten a lot of meat. You've just had one or a couple of bites. Similarly, this talk will give you a broad understanding of the field without diving too deep or pretending to give you the whole bird. So, in some sense, we're just dipping our feet in the water. Also, I love chicken wings, and I just needed an excuse to pull that into this talk. So, here we are, clucking along. In this talk, we will learn what AppSec is and how it is applied to secure software engineering. We'll look at a fictional example of insecure code development and contrast that with SecDevOps or DevSecOps, so we may all leave here with a better appreciation for the role that application security plays in modern software engineering. But first, a word from our sponsor. Have you ever felt like there were way too many social networks to keep tabs on? Like there needed to be a better consolidation of our feeds so we can spend less time in front of our screens and more out in the real world? Psh, of course not. Presenting the newest antisocial network, Tatter. Tatter is launching soon on the web, mobile, AR, VR, and everywhere else your Wi Fi network reaches. Sign up for an account or multiple accounts today. Tatter, it's where your friends aren't. Now, to be clear, Tatter is entirely made up. It's not a real company, it doesn't exist. There is no alternative anti-social network called Tatter, regardless of whether Arrested Development would like you to believe that through the usage of hacker traps and other things like that, there is such a thing. In our case, it's completely made up, but we can use it as a very useful case study to see how the Tatter team, in one iteration, cut corners in software development and the consequences of those actions. And we usually only get this kind of hindsight with an Equifax breach or a Yahoo breach. Let's instead learn from Tatter and their missteps. Then, once we have seen that play out, let's time travel back in time and fix things by ensuring that Tatter follows AppSec practices and extrapolate that story arc to see how it ends up. Now, Tatter started as an anti-social network from an Ivy League college where a bunch of students got together and started writing code from their dorms. They were able to leverage their connections with venture capitalists to get funding to hire more engineers so that the VCs could, as I emphasize it, increase velocity. Freshly funded and on a full belly of VC money, Tatter hired engineers to add more features. They added a dislike button, photo uploads, advanced search, and many other features. In the race to launch publicly, many corners were cut. Technical debt accrued. The focus was on velocity, not veracity. Mistakes were made, but they weren't caught yet. As Tatter grew, they added a marketing department, legal department, and inevitably HR department, limiting their engineering workforce to just developers. They just wanted to focus on getting the product out the door. Things were looking good for a product launch soon. The founders were happy, the VCs were happy, the engineers, let's just say they were happy because this is all hypothetical anyway. From a soft launch to an open launch, Tatter saw increasing consumer usage and engagement. In their first months, they grew the user base, all while it focused just on growth. However, as these things tend to play out, one fine Friday evening at 4 o'clock in the evening, news broke that Tatter was hacked. The news spread like wildfire, picked up by major news outlets. The Tata team would have to pay up their technical debt, it seemed. As news of the hack spread and as time went by, we're now at a timeline ahead of when they were originally hacked. So let's spend a few minutes learning how Tatter was hacked. This will give us insight into everything that went wrong at Tatter itself. And to understand this better, let's just look at a high level architecture diagram of everything that it involves. Tatter just had a client, so it was either a mobile client using the app or the browser on a desktop machine, communicating using an API which allowed clients to interact with the backend. In the backend, we've simplified it here as a database, which is where the user data is stored for the antisocial network. Now let's pick these apart piece by piece to see the entire kill chain of how they went from initial breach to outright ownage. Let's start with the mobile apps. Tatter was meant as a mobile first anti-social network. The focus of the engineering team was around the mobile user experience, with a lot of attention paid to the visual design more than the entire architectural design of the app itself. As a result, many shortcuts were taken to launch and get the apps reviewed and published on time. One such shortcut was that the API key used to communicate with the backend using the Tatter API was stored in the code of the app itself as a string in the resources file, in fact. So when the app was published in the app stores, especially on Android, you can download the APK and disassemble it to look inside it. Hackers did just that. They got hold of the APKs, they cracked it open. They were able to extract the resources from reverse engineering the app package to find the API key, because you can find strings inside the strings.xml file when you open up an APK file. So they had one secret. Additionally, let's look at the API. When signing up for a Tatter account, a user is prompted to enter their email address as part of the sign up process. We're all familiar with this. This is very normal. However, if an account already existed that used the same email address, Tatter would prompt the user to sign in instead. Even at this point, we're feeling comfortable that, okay, it's information disclosure at some level, but how bad can it be? Well, the username was pre-populated that matched the email address entered. Now, even at this level, if it feels like a convenience, you realize that anybody can abuse the API and cycle through a bunch of email addresses and find the associated usernames. And to use this API, you need the API key. Hackers already had that from reverse engineering the mobile app. So they were able to cycle through a bunch of email addresses, find a bunch of usernames. Using the API, which coincidentally was not rate limited and did not lock out after a bunch of failed login attempts either. So using automation, they could find many usernames and crack a bunch of passwords. And password cracking, they could have used password spraying, they could have used credential stuffing. The point of the matter is, with the API key and insecurity in the design itself, without rate limiting and things like that, they now had a bunch of usernames, not starting from the emails, and their passwords which they were able to crack. Now let's switch our attention back to the website. A given user's profile on tatter.com could be navigated to using their username. So it was a URL like tatter.com/users/username, so /John Doe, for example. From the list they obtained by abusing the API, now they had a list of usernames, so they essentially had a list of URLs that pointed to valid profile pages. And again, abusing the API without rate limiting, hackers were able to scrape the profile pages of many users, including that of site admins. And the reason they were able to do this was the accounts were registered to guessable email addresses like admin@tatter.com. The username may have been different, but essentially were able to get that from the API itself. And additionally, the admin accounts, many of them used poor password choices and they were easily cracked. So hackers were able to sign into the admin accounts using just the username and password and view all profile metadata. Now you might be asking, so what's the big deal if someone logs into a nascent antisocial network with a username and password and they see 5 posts? Well, password reuse is a problem. So let's talk about source code. A lot of the source code, in fact, all of the source code for Tatter was hosted on the private GitHub repo, and the email addresses and the passwords used for GitHub was the same as the ones they used on Tatter. So they reused both the emails and passwords between their Tatter accounts and GitHub. And in the case of their GitHub setup, there was no two-factor or multi-factor authentication either. So hackers were then able to get access to the entirety of the source code for Tatter, product code, internal infrastructure code, everything. And in there, they found more nuggets. They found database connection strings, they found cloud storage account connection strings and other credentials, so many other secrets in code and more. Using the newly discovered credentials, hackers were ultimately able to breach, access, and exfiltrate the cloud stored customer data. Additionally, reminiscent of the Yahoo breach, Tatter also stored customer passwords as MD5 hashes. They did not use a more secure hashing algorithm. So, by exfiltrating the MD5 hashes, hackers were also able to crack a large number of customer passwords, which we just revisited the problem of password reuse. These passwords are also invariably used in multiple other sites with these user accounts. So you end up having the username and passwords for so many users, not just on tatter.com, but potentially their banking websites and so on. This was huge. The keys to the kingdom was theirs, and Tatter did not have a clue. What was the outcome of all of this? For trivia, the photo you see on screen is an image of the wildfires in California from last year, as seen from the International Space Station. You see all the smoke emanating from the forests which are on fire, going off the coast into the Pacific Ocean. And this is what happens when a fire goes unchecked till its impact is so massive. Now, if you could anticipate that a certain set of actions was going to result in a massive wildfire, now let's say you saw somebody lighting a match and you knew they'd start a campfire, which you could foresee would go out of control and set fire to the forest. Would you extinguish the flames when the match was lit? Would you extinguish the flames when the campfire got out of control? Or would you wait till millions of acres were burning? It is a rhetorical question, but it has to be asked. So we see Tatter ended up in a bad place by rushing the design, by using insecure development practices, poor implementation, and ultimately, for the sake of our discussion, without an application security program. Let's switch gears and talk about the application security program itself. Let's talk about starting with a software development lifecycle, the SDLC. We're all aware of it. We decompose the entire development process into stages. Traditionally, in the case of a waterfall model, which, by the way, the image you see on screen is that of Multnomah Falls just outside Portland, Oregon. The SDLC traditionally comprises an initial requirements phase, followed by a development phase, then a testing phase, and then release. In this traditional model, testing, especially security testing, happens only if the product has been built to some degree of maturity and usability, not earlier. Application security is the process of finding, fixing, and preventing security vulnerabilities at the application level as part of the software development process. This manifests as multiple parallel processes that aim to find and address issues early in the SDLC. This is also called shifting left because we're essentially shifting the testing, specifically the security testing part, left in the SDLC. It doesn't happen specifically after development. It runs in parallel with requirements gathering, with design, with development, with testing. There's aspects to each of these so we can catch issues early, so we can extinguish the flames before we end up with a wildfire. And here are some of the things that are generally part of an AppSec program that we'll look at kind of at a high level, but should give you an appreciation for the role that AppSec plays in software development and an understanding of the processes themselves. Now let's travel back in time to when Tatter began as an idea. We saw how their lack of an AppSec program and insecure practices ended up. So let's travel in the time machine, let's infuse application security into their engineering processes, and follow that development and see where they end up, using some of the processes that an AppSec program uses, which we just saw. We know there is a requirements phase as part of the SDLC. Similarly, an application security program might have a security requirements phase where you have personas, you have user stories, you understand the security requirements and lock down the security controls. You understand to make sure that there are security controls. I'll be very brief about this, but the traditionally more prominent and aware parts of application security that people see, especially engineers, is a things like threat modeling. So as part of the system design, since we're in Tatter 2.0, Tatter developers and security engineers are collaborating on a threat modeling exercise to identify the key assets that need to be protected. Once you identify the assets, you recognize trust boundaries between the internal assets and external actors, and you ensure that appropriate controls exist to secure your assets against external threats. Now, since we're working hand in hand between developers and security engineers, to keep the content approachable to all collaborators, a diagrammatic approach is used in the form of what's called a data flow diagram, a DFD, where the flow of data from external users through internal infrastructure is followed. As the data flows from external to internal and potentially back, you identify a bunch of security risks, you identify a bunch of threats, you identify controls to make sure that those threats are monitored, mitigated, reduced, or eliminated. And threat modeling is used to ensure that controls exist to prevent things such as spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. The six that I have rattled off, you can remember it using the STRIDE acronym: S for spoofing, T for tampering, R for repudiation, I for information disclosure, D for denial of service, and E for elevation of privilege. Once threat modeling is done as part of the original design, part of the SDLC, and code starts being written, code reviews come in handy to try to catch things early if they have been missed so far, or to catch issues in business logic where the design is secure but the implementation is flawed. So code reviews are an essential part of any collaborative software development. If you're writing code, you're probably, hopefully, getting that code reviewed before you check things in. And when you have code you think is ready to be checked in, you seek review and approval from your peers. That's normal for normal code review as well. A security focused code review is more focused on the security controls. It's not that security engineers are trying to understand the implementation itself, but anything specific to security, they want to make sure it's implemented correctly, it's implemented in a standard way, in a safe way. This is where you try to catch things like custom crypto instead of using standardized cryptographic algorithms and libraries. And it's a very effective way to get an extra set of eyes on any new code that's being added. Now, at this point, we have gone through the requirements, we've gone through threat modeling, we've gone through a code review. Let's assume for some reason there's still things that are missing. So Tatter's gone through things it hasn't done in Tatter 1.0, but it's done in 2.0. It's caught a bunch of issues, but nobody's perfect, or should I say, nobody's perfect. So issues have gotten in and have been checked in. Now, this is where you use something like a static application security testing tool suite, or a SAST. So once the code's been committed to a product's code base, additional sets of tools are used to scan this code. So a SAST tool can be used to find security issues that might have been missed in code reviews. So things like secrets in source, which we'll get to in a little bit, and we'll talk about that, about how you can use regular expressions and entropy to try to find those things. Insecure query construction, where you're not sanitizing user input, we'll look at that as well. And on screen you see the image where I've used a security vendor's product that scans GitHub repos, and I forked the OWASP juice shop repo and I've run the tool against it. You can see it flags a whole host of security issues based on criticality. It classifies them as critical, moderate, and others. It's also found secrets in source. It has a bunch of other insights. It's very useful to incorporate a SAST tool as part of your continuous integration pipeline. So as code gets committed in, you're monitoring the hygiene of incoming code. Now, what are some things that a SAST can catch? One great example is memory safety issues, especially when it comes to unsafe functions. Now, the function might work logically, but it might be flawed in its own internal implementation. And these are things that could be missed in a human code review. So, as an example, the C function string copy, strcpy, which is used to copy a string from a source to a destination. It is an unsafe function because it doesn't check if the destination has enough space to store the source string. And if the source string is larger than the destination string buffer, it'll overflow the bounds, and this can lead to a buffer overflow, which may be exploited. So if such a documented unsafe function is used, a SAST tool will flag it, and there's steps to remediate this to use a more safe function. So this is one class of bugs that can be found and stopped. In fact, MITRE just came out with their list of the most critical bugs or vulnerabilities that have been used in recent past, and buffer overflows or out of bound writes was the highest by a long shot. So if you can even cut down some percentage of that, it's better than nothing, right? You also have things like input sanitization, where you're seeking input from a user and you're taking it as face value without potentially sanitizing the input, passing that in as a parameter or an argument to another function you're calling, which could lead to unintended consequences. This is how you end up with cross-site scripting. This is how you end up with SQL injection, where you don't sanitize the input. You don't create a parameterized query, for example. You don't get rid of the HTML content that could be passed in as textual input, which you then potentially pass on to vulnerable functions. So catching this class of issues as well, because SQLi and XSS has been a fairly large scale set of issues for a long time now, and tools, SaaS tools especially, are able to flag some of these issues. We've talked about secrets in code a few times now, but why is this such a big deal? For any or many intermediate processes that an app does, security is a big part of those transactions, and often the security depends on the usage of a secret of some sort. So this could be an API key, an SSH key, an OAuth token, etc. Committing any of these into source is dangerous due to how easily they may be found, as we saw with Tatter. Tatter had it in their mobile app, they also had it in their private GitHub repos. To store these secrets securely, use a key vault or a secret store, which allows programmatic access and retrieval of the stored secrets versus hard coding it in the code itself. And the point here is there is no such thing as a partial secret compromise. Any accidentally disclosed keys need to be changed. I will add, even though it doesn't fall under the purview of application security per se, the choice of strong, secure passphrases over weaker passwords. Enough with the password 123s, enough with the 12345s, the let me ins. Let's move to more secure passphrases. Additionally, in today's complex interdependent software systems, where your code interacts closely with other code from dependent libraries, it's important to protect the full tree of dependencies. It's possible that the code you wrote is secure, but you are dependent on an insecure library. Software composition analysis, SCA, is used to better understand the dependencies that your product uses, and this is also something that a SaaS tool can find. So once you have done SAST scanning of code that's been checked in, and you have, through your continuous deployment pipeline, a build that contains these new changes, or a version of it you can use, we can move to something that's a little more dynamic in testing, where you're actually testing the product as it's being run. And one such thing is fuzzing. And let's understand fuzzing with a joke which I read a while ago. It goes this way. A QA engineer walks into a bar and orders 1 beer, 2 beers, 100 beers, -1 beers, 1 bear. An actual customer walks into the same bar and asks the bartender where the restroom is located. The bartender halts and catches fire. Fuzzing is the process of feeding a system unexpected input to see if it can handle the unexpected input appropriately, and if needed, fails gracefully and safely. So when you have a build of your application under test, you can pass various sets of fuzzed input, and there's multiple sets of tools that let you create fuzzed inputs, whether it's an API or whether it's an actual set of inputs itself on the web app or any other app, for any code really, where it's taking input from a user. Instead of generating expected input, you can generate unexpected input, pass it in, and see what happens. We've seen SAST, we've looked at a static application security tool. What about a DAST, a dynamic application security testing tool? Since you have a build, since you have a version you can play with, you can scan it, you can find out or try to find out using spidering all the different places that you can interact with it. You can try to, we just saw fuzzing, but not true fuzzing, but there's a way of passing in a range of inputs to the application to see if it behaves differently. And on screen, we have one free open source popular intercepting proxy, OWASP ZAP, the Z attack proxy. There's also the proprietary but very popular Burp Suite. And these are both intercepting HTTP proxies where any requests from browser on that machine can be intercepted, and you can at some level use it as a netcat-esque tool where you can pass it into the repeater or the intruder and mess with the parameters or the request itself. Now we've seen, starting with requirements, threat modeling, code review, using SAST, using dynamic testing and fuzzing, we're so far ahead of the curve compared to Tatter 1.0. And in this version of Tatter, in this version of reality, Tatter launches successfully. Its customer data is kept secure thanks to early identification and remediation of security issues. This was a result of a good application security program that worked with DevOps to prioritize product security and shift left successfully. Tatter was praised for its privacy and security, and over time gained enough users and revenue to allow its CEO to purchase a ticket to space in the near future. The outcome in Tatter 2.0 is that Tatter had a good run the second time around. They had a successful AppSec program that allowed them to find and fix security issues when the impact and cost were still low. This is a far cry from the wildfire of Tatter 1.0. In summary, and by the way, this is a great bit of visualization from Tanya's book, Alice and Bob Learn Application Security. On the left, you have essentially the flow of the SDLC, starting with requirements design through test and deployment. On the right, you have application security processes that occur in parallel with the SDLC, relevant to that stage of the SDLC. So you have security requirements. For design, you have threat modeling, design reviews. For code, you have code review and SAST. For testing, you have SAST, DAST. Pen testing, when you have more idea about and a bit deeper understanding of the product itself. So by injecting and standing up an application security program parallel to your SDLC, you're going to be much better off from a security standpoint. A couple of other things I wanted to touch upon. All the issues that we saw Tatter have with their 1.0 are part of what is known as the OWASP Top 10. The OWASP organization, OWASP stands to the Open Web Application Security Project. And it's an open source group of security volunteers who come together to identify the top threats to web applications. They come to identify not just web applications, but APIs and other attack surfaces as well. They identify testing guidelines, and the OWASP Top 10 is a list of the top 10 critical issues that web apps face on the web today. And we saw things like injection, we saw things like authentication issues. They're all part of the OWASP Top 10, so I highly recommend checking out the OWASP Top 10 list to understand the top 10 critical vulnerabilities that your web app or API or so on can face. Another project I'd like to highlight from OWASP is the OWASP Juice Shop. And the OWASP Juice Shop is a purposefully vulnerable web application based around an e-commerce marketplace. This is what it looks like. Think of this as like an online shopping website that has specific vulnerabilities for you to find, almost like a CTF. So here's an example. there is what they call a shenanigan. You have multiple types corresponding to different points of the OWASP top 10. So you have sensitive data exposure, you have cryptographic issues, injection, insecurity, serialization, and in the OWASP Juice Shop app, you can use it as your own CTF at home to find these issues. And what's even great about this is when you find one, you can also look at the actual code that is vulnerable. So, for example, here for this for this XSS vulnerability, I see that there is a bypass security trust HML function, which should not have been used because that is the root of that vulnerability. And just for fun, using the same vendor's SAST tool and forking Juice Shop, I ran it against the Juice Shop source code, and I found a bunch of, or the tool found a bunch of issues. It found secrets in code. One caveat I will call out about SAST tools is that it tends to have or tends to surface false positives where you think they are actual issues, but they are not, and then there needs to be manual triage to find and validate that they are legitimate issues or not, because you don't want to bombard the development team with here's 50 bugs, and it turns out maybe only 4 or 5 of them are actually legitimate and the others aren't. Here's another screenshot of a couple of the critical ones. I, I see that it says HTTP data to SQL database, points out the line of code in the file. I open it up since it's a GitHub project. I see that a parameter from the request body is concatenated and added on to my database query. So I can use SQL injection to escape the rest of the query and exfiltrate data or get access to more data than was designed at that point. It's also flagged a bunch of secrets. So for example, in code, there's a private RSA private key committed to code, which is not a good idea. We saw what happened in Tatter 1.0. Again, these are the kinds of things that a SAST tool can find out. So having seen everything that we have seen for an application security program and how it parallels in SDLC, a couple more resources I wanted to leave you with. Tanya has a great book titled Alice and Bob Learn Application Security. It is a very well structured look at AppSec from how you look at it from a design phase through the development phase, through how you stand one up, through how you apply it to different types of applications themselves. The Tangled Web is an amazing book as well, which looks at web apps, web traffic, and HTML at some level. HTTP is what I wanted to say. And when it comes to threat modeling, Adam Shostak's book, Threat Modeling Designing for Security, is a very well structured book to understand and ramp up and get familiar with threat modeling as an exercise. I hope this session has given you a better appreciation for the value that application security adds, especially when run parallel to secure software development. To learn more, please visit tatter.dev. It includes the notes we've used so far, including a transcript for internationalization and accessibility. In closing, I want to thank you for attending my talk. Take care, stay safe, and keep hacking. Thank you.